Today I want to discuss the normal distribution. A normal distribution is a probability distribution. So the first question you want to ask is, what is a probability distribution? Well, a probability distribution is, for lack of better words, a distribution of probabilities of an event that you might be interested in or a quantity that you might be interested in. So essentially there are two types of probability distributions. One is a discrete probability distribution. That's the one you see on the top. Discrete. And there is another type which is the continuous probability distribution. In the discrete probability distribution, you have the probability on the y-axis. What you see here is the probability, and on the x-axis you have a quantity for which you are interested in finding the probability for. Say for example, there is a match between Germany and Argentina, and you want to know what is the probability that Germany will score either 0 goals or 1 goals or 2 goals, 3 goals or more than 3 goals. And for each of these possibilities, there is a probability assigned in the probability distribution. So for 0 goals, you have a 25% probability. For 1 goal, you have a 30% probability. For 2 goals, you have a 23% probability. For 3 goals, there is a 15% probability. And for more than 3 goals, there is a 7% probability. And the thing to note here is that these probabilities are collectively exhaustive, which means that if you add them all up, you get 100% or 1. So now if somebody asks us what is the probability that Germany is going to score less than 3 goals. So we have 3 cases where the number of goals is less than 3. It's this one, 0 goals, 1 goal or 2 goals. And let's add their probabilities up. That's how a discrete distribution works. You just sum up the probabilities of the individual events that form the event for which you want to find out the probability. The event in our case being probability of scoring less than 3 goals, right? And it is 25% plus 30% plus 23%, and that turns out to be 78%, right? So we just added up the individual probabilities, 25%, 30%, and 23%. Okay, so then coming to the continuous case, which is the chart below here, this one. There is a subtle but a very important difference between the graph of a discrete probability distribution and a continuous probability distribution. So in the discrete case, you see that along the y-axis, you have the probability itself. And in the continuous case, along the y-axis, you have what is called the probability density. And often while teaching probability in schools or in colleges, this difference is not emphasized clearly enough, that the probability and the probability density are different mathematical entities, and they are not bound by the same rules. So for example, the sum of all the probabilities in a discrete distribution is 1 or 100%, as we have seen here. But there is no such cap on the probability density in the case of a continuous distribution. So for example, if we take this density, which is along the y-axis, and we map it to here, it could be anything. It could be 5, it could be 6, it could be 7. It doesn't have to be capped at 1. Because the probability density is not the probability. It is something else. It is not in the scope of this video to explain what the probability density is, but just suffice it to know that it is not the probability. And now proceeding further, if you want to know, in the case of a continuous distribution, the probability of the event that you are interested in. So for example, you have invested a particular amount of money in stock A, let's say it's $50, and you want to know what is the return that you can expect. And you want to know what is the probability that you will earn either a 3% return or a 5% return or anything in between. So as opposed to the discrete case where you just add up the probabilities, in the continuous case, the probability of the event that you are interested in within these intervals is the area under the curve within these intervals. And why the area under this curve within these intervals, well, that's again an advanced topic, but just suffice it to know whether it is a normal distribution or any other continuous probability distribution, and you want to know what is the probability of an event within a given interval. It could be some other interval, it could be this interval. You need to find the area under the curve within that interval. That will give you the probability that you're interested in. And for our purposes and the purposes of the video, this knowledge is enough. We don't need to know the deep math or the derivation or the philosophical probability theory behind why the area under the curve is the probability of the event within these intervals. And just like in the continuous case where the sum of all the events is 100% or 1, as we see here, in the continuous case too, if you take the entire area under this curve, the entire area from the start to the end, this area is equal to 1. So that's a good analogy between the discrete and the continuous case. In the discrete case, the sum of all probabilities equals to 1, and in the continuous case, the total area under the curve, which is the probability of all the possible intervals that the variable for which we are interested in calculating the probability for can take, is also equal to 1. Okay, so now let's see what we have learned here, how this applies to the normal distribution. So this is what a normal distribution looks like, the figure that you see on the right, and it's probably clear to you now why it's also called the bell curve, because it looks like a bell. And on the x-axis you have the value or the quantity for which you are interested to find out the different probabilities for, and the normal distribution is defined from for x equals to minus infinity to plus infinity. Not all the continuous probability distributions are defined from minus infinity to plus infinity. Some are defined on x equals to 0 to 1. Some are defined from x equals to 0 to infinity. But the normal distribution is defined for all values of x from minus infinity to plus infinity. And this is an important fact to bear in mind, because the normal distribution is used to model quantities like the average rainfall received in a month for a particular city, or the stock returns. And the average rainfall cannot be negative. It can be 0 minimum, but not negative. It's not like you can have minus 5 centimeters of rain in a year in a city. That does not mean anything. Similarly, if you are modeling your stock returns using the normal distribution and you have invested a particular amount of money, the lowest return that you can have is minus 100%, which means you lose all the money you invested in the stock. The stock value went to 0. But it does not make any sense to have a stock return of minus 120%. What does that mean? You cannot lose more money than you invested in. So that is something to keep in mind. But the way the probability distribution would be defined for those quantities is that when you sum up the area under the curve for those negative quantities, for example, if you are saying what is the probability of receiving rainfall between minus 5 centimeters and 0 centimeters, that area would be so negligible that you can ignore it and you can continue to safely model the rainfall as a normal distribution. So that is something to keep in mind. If it doesn't make sense what I just said right now about modeling negative quantities, don't worry. When we jump to the numbers in the Excel sheet, it will become amply clear what I'm talking about. And you may have probably already noticed that the normal distribution is a continuous probability distribution. So what we have discussed is some time back, the differences between the discrete probability distribution and the continuous probability distribution. So the normal distribution is a continuous probability distribution, which means that on the y-axis, on this axis, you have the probability density and not the probability. And the probability density is given by this weird looking formula over here. And the first time that I saw this formula, I didn't know where it came from and how someone dreamt up of this formula. Why not something else to describe the bell shape? And if you look up on the internet, you will find ample number of resources, documents, and videos that explain how this formula is derived. But even if you don't want to know that derivation, that's okay. You can still continue to use the normal distribution to determine probabilities of the events that you are interested in. But it's good to know that this is the formula. And the y that you see here is the probability density. This y over here on the left is the probability density. And as you keep on plugging the values of x into this formula here, as you keep on putting the values of x in the formula here, uh, let's say for example, I want to know what is the value of y if I put in this value of x. It can be, let's say, I think it could be 2, let's say, and then you get a value of y here when you plug it into this formula, and then you can plot out this curve. There are two more quantities I would like to talk about that you see in this formula. One of the quantities is sigma that you see over here, and the other quantity is the mu that you see over here. This is a Greek letter mu, and this one is the Greek letter sigma. So first let's talk about mu. Mu is the value of x around which this distribution is symmetrically distributed. So you can see that if I plug in the value of x as mu, then I get the highest density for this distribution, and the distribution is sort of symmetrical around this point. And then there's sigma, this quantity that you see here. Sigma gives you an idea of the spread of the distribution, which means that how spread out this distribution is, how wide this bell shape is. If you have a big sigma, your distribution could be more spread out, which means it could look like this, right? Not a very nice sketch, but you get the idea. And similarly, if your sigma is small, your distribution could be less spread out and it could look like this. So that is the intuitive explanation of mu and sigma. We'll look at it when we play around with the numbers in Excel. But just so that you know that when you are plotting for a range of values of x in this distribution, your mu and sigma are generally fixed, and they generally come from your historical data. So for example, if you're trying to model the rainfall in a city using the normal distribution, you would probably have the last 100 years of rainfall data, and from that data you can calculate the mu. Say for example that mu could be 5 centimeters, and you could also calculate the standard deviation, which is sigma, which could be, let's say, 2 centimeters. So you know your mu and sigma from your historical data. Those are fixed, and then you plug in the values of x as we have discussed earlier into this formula over here. Over here you keep plugging in your values of x and you get the plot of your normal distribution. Okay, so now let's get these pictures aside and let's look at how to plot the numbers in Excel. All right, we are in Excel now, so we are going to plot the probability density function for the normal distribution. As we have seen earlier, the probability density function accepts 3 parameters. One is the parameter mu that we see here. One is the parameter sigma that comes in here and here. And the third is the set of x values for which we want the probability density function for. So in our case, I'm just going to fix the value of mu as 25. It can be anything, but just for this example, I'm going to put it as 25. I'm going to put the value of sigma as 4. And in this column B, starting from this row number 8, I have the values of x for which I want to plot the probability density function. So you can see these values are equally separated from 5.4 to 5.6 and then to 5.8. Each value is separated from its previous value by a difference of 0.2. So this will help us to get a very smooth plot of the function. And so let's begin. So one of the ways to get the probability density function is just to implement the mathematical formula for the probability density function, that which you see here, just as it is in Excel. So I have color coded the different parts of the formula here and accordingly put them here. So if you just want to compare, you can pause the video and compare that the formula in Excel is the same as the formula in terms of the mathematical Greek letters. So I will just copy this formula here and I will put it here. So you can see it is accepting three parameters. It's accepting the value of x, which is row or which is cell B8. It is accepting the parameter mu, which is in cell C2, and it is accepting the sigma parameter, which is in cell C3. And let me go ahead and press enter. Okay, so that is one of the ways of getting the value of the probability density function. One of the other ways is to use the inbuilt Excel function norm.dist, which is nothing but the implementation of the formula as well. So I'm going to enter it here. So you see it is also accepting the x value as a parameter, it is accepting the mean as a parameter and the standard deviation as a parameter. And I'm going to press enter, and there you go. Both these values are identical. Whether you implement the PDF formula yourself in Excel, like the way I have done over here, or you use the inbuilt Excel function norm.dist, you get the same value. And I'm just going to double click here so that the formula is replicated for all the rows in these two columns. And you can see that the values are same, whether you use the formula on your own or you use the inbuilt Excel function. For all values of x, you get the same value of y. Okay, so let's just go ahead and plot the value of y to see whether we have got a normal distribution bell-shaped curve or not. So I'll go down, press Ctrl Shift and press the up arrow key, and I select all the values in this column. I'll go to insert, I'll go to charts now, and I select the line chart. Yeah, there you go. This is what we were expecting, and this is what we have got. This is the shape of the normal distribution for a mean of 25. And okay, so when you plot a chart in Excel, by default it gives the serial number of the values. If you want it to reflect your actual x values, you have to go and select data, and for your horizontal category labels you have to select your x values. Okay, so now I have my x values. So you can see that the distribution is centered at 25, which is our mean value or our mu value, and it has a standard deviation of 4. Okay, so let's have some fun with this distribution. Let's see how it changes if we change the value of the mean and the standard deviation. So just to get a reference, I'm going to insert shape here. Let me put a line here to mark the mean, so that if we change the mean to some new value, we know how the mean is moving. So right now we can see the mean is at 25, even though 25 is not written here, but you get an idea that after 24.6 you are going to have 25. And let's just also use a line to mark the width of this distribution at this level, just for reference. And we'll see how the distribution changes as we play around with the mean and the standard deviation values. So let's say if I change the mean from 25 to 20, so you see the highest point in this function has moved from 25 to the new value, which is 20, somewhere around here 20. The earlier value was here at 25, it has moved to 20. So let me make it back, change it back to 25. Okay, and now let's see if we can make the curve thinner by changing the value of the standard deviation from 4 to 2. I put 2 here, and I see that the curve has become thinner. Earlier it was spanning from this point to this point, and now it's spanning from here to here. And if I change it from 2 back to 4, we have our original curve. And if I change it to something bigger, let's say 8, now we see that the curve is much more spread out. Okay, I'm going to plug back the value of standard deviation equals to 4, so that we return to the shape of the distribution that we started out with. Let me get rid of these lines since their purpose is already served. And now what we are going to move into is calculating the probability of an event that we are interested in by calculating the area under the curve. Okay, so let me just stretch out this axis, the x-axis. Okay, let me stretch it out even further, and I'm going to zoom in to 400%, so we get a really good picture of the curve along with the x-axis. Okay, now so let me take an example. Let's say we are interested in finding out the probability that the city receives rainfall between 18.6 centimeters and 20.4 centimeters. Let's say it's this dot and this dot, 18.6 and 20.4 centimeters. And I want to know what is the probability of that event. So let's just say 18.6 is your value x1, and what you have for x2 is 20.4. So x1 is 18.6 over here, and x2 is 20.4. And when you plug in these values into your normal distribution formula, you get the y values. Let's call this value y1, and when you plug in x2, you get this value on the plot, and let's call this value y2. And the probability that the rainfall received is between 18.6 centimeters and 20.4 centimeters is this area. It looks like a trapezoid, or maybe it also looks like a rectangle. Maybe we can approximate the area under the curve by treating this shape as a rectangle. So what we can do is we can find out this height over here, and that could be said to be y1 plus y2 divided by 2. That's the average height of these 2 points, this one and this one, somewhere in between. And let's use this value of y to construct a rectangle. So the area of this rectangle is a good approximation of the area under the curve between these 2 points, because while you are taking up some extra area over here which is not under the curve, you are also giving up some area here which is actually under the curve. So this rectangle seems to be a good approximation. So the breadth of this rectangle can be said to be x2 minus x1. x2 minus x1 is the breadth, which is this value, x2 minus x1. And the height of the rectangle, as we have already seen, this one is y1 plus y2 divided by 2. So this expression over here is going to give us the area under the curve for the interval that we are interested in. And I want to add 2 things over here. The first one is that if you scroll to the left and you see that as your values of x start getting smaller and smaller, so for example, if you want to know what is the probability that the rain received will be between 7.8 centimeters and 8.4 centimeters. If you draw a rectangle over here, it has no height, means there is no area under the curve over here. The probability of receiving rain between 7.8 centimeters and 8.4 centimeters for this distribution with a mean of 25 and standard deviation of 4 is practically 0, which means that you are very, very unlikely to see that the rain received in the city in a given year is going to be between 7.8 centimeters and 8.4 centimeters. And this relates back to the point that I was alluding to earlier, where I was saying that a normal distribution stretches for values of x from minus infinity to infinity. So if we keep on going left over here, I have just taken values of x till 5.4, but if you keep on going left, the values will get smaller. It will go to 5.25, and at one point it will touch 0, and it will go even below 0. And just like the cases over here, the probability of getting negative rain, which in the first place doesn't make any sense, there is no such thing as negative rainfall. But even if we consider that case, that will be 0, almost 0, because the area under the curve for those points will be 0. So I'm again restating that it's safe to use a normal distribution to approximate rainfall, because negative rainfall, even though it is impossible, the probability assigned by the distribution to those cases is also 0. Okay, that is the first point that I wanted to talk about. And the second point is, first let me get this formula slightly to the side. Okay, let me just pull it out over here. Okay, so with the formula out of the way, the other point that I want to make is, for this example, I've taken a very wide range so that I could draw properly here and show you how y1 and y2 and y1 plus y2 divided by 2 work out. Generally, when you are given such a wide range where you want to know what is the probability of the rainfall being between 18.6 centimeters and 20.4 centimeters, you don't generally use one big rectangle. The way it is done in statistical softwares is, let me just choose a pen here. This range is broken down into further smaller ranges, like this. Smaller ranges like this. And the area for each of these smaller ranges is calculated and added up. And that is done because the smaller your rectangle, the better the approximation of the area under the curve. So let me take an example of a big rectangle and show you why it's a poor approximation. So let's say I want to find the probability of the rain being between, what is this, 21.6 centimeters and 28.8 centimeters. So if I want to find the probability of rainfall being between these two quantities, 21.6 centimeters and 28.8 centimeters, I can't just take this rectangle, this big rectangle, and say that that is the area under the curve, because clearly you can see that this area over here is being left out. It's not a part of the rectangle. So the way to do it is, let me again take a separate color. Let me take green. If you want to find the probability of rain being between these 2 points, you have to take small areas like this. So you get the point, right? And then find out the area for each of these rectangles, small rectangles, and then sum it up. So if I have to say it in terms of this formula over here that we see here, what I'm trying to say is that your x2 and x1 should be as close as possible, so that the area of the rectangle will be a very good approximation of the area under the curve between x2 and x1, if your x2 and x1 are very close. That being said, now I'm just going to copy this formula over here, and I have this formula. I want to copy it, and let's go back to a reasonable zoom level. Let's go back from 400% to 200%, and let's go back to our table. Okay, I just realized I don't need to actually copy the formula. We can paste it here. So now I'm going to use this formula to calculate the probabilities in our table. So let me just write down what the x2 and x1 and y2 and y1 are here in our case. So this is for this cell over here, for this cell, this is going to be our x2, this is going to be our x1, this is going to be y1, and this one is going to be y2. So let's just go ahead and apply the formula. Okay, let me write here equals to x2 minus x1 into y1 plus y2 divided by 2. Okay, that's a very small area, because we know at this point 5.4 and 5.6, we can see here in the graph, the height of the graph is almost close to 0, so the area under this curve is also close to 0. So I'm just going to double click here so that the formula replicates for all the values of x, for all the intervals in x. So just to reiterate, what I have done is for our distribution that we have here, the distribution, I have broken it up into small intervals, and I have calculated the area for each of these intervals. So what you see in column E over here, these values which are underlined, these are the areas for all the small intervals. And let's just to be sure that the calculation is correct, let's just check whether this area sums up to 1, because as per our theory, the total area under the curve should be equal to 1. So I'm just going to take sum of this number till the end. And you might question that I'm not taking values of x from minus infinity to infinity. I'm just starting from 5.4 and going up to 44.4. But as I've shown you earlier, towards the tails, the probability or the area under the curve becomes so small that you can safely ignore it. So let me just sum up the other area, and let's see. Okay, so it's pretty close to 1. It's 0.999999. So far we are going all right. Okay, so the next thing I want to show you is that when I had earlier copied the function, the inbuilt Excel function for the normal distribution, this was the formula that I had used, and you can see at the end there is a parameter false. And at that time I had not explained what this false means, and you can use true also. And now I'm going to explain what's the difference between using true and what is false. So if you use the false option, and when you enter an x value, let's say I enter a value of x over here, I'm marking it on the distribution, the output that I get is this value of the function. But if I use true as a parameter in my function, when I use this true, And when I enter an x value, what I get is not the density value, but what I get is the area under the curve till that x value. This area, if I use true here as a parameter instead of false, which I had used earlier. Okay, so repeating myself here, just to be clear, to avoid any confusion, if this is your distribution and you use the norm.dist with false option and you enter an x value, the value that you get from the function is this point over the x value. This, what we have discussed earlier, is the probability density. But if you use the true option for this x value again, now what you get is not this density, but instead you get the area till this point. You get the area till this point. So that is the difference between using true and false in the norm.dist function. So let's check. We know that our mean for the distribution is 25, which is over here. And if I use the true option with x equal to 25, the area I'm going to get is still here. And looks like if I plug in 25, I should get 50%. My area that I'm covering under this curve is half. It should be 50. So let me just go ahead and copy this formula over here. Okay, I'm going to copy this formula. Okay, copy, Control C, and let me go back and let me find where the value of x is 25. Okay, it's here. Let me paste this formula. And I have to change it from B8 to B106. B106. Okay, so this is the value of x that's going in, and C2 and C3 are my mean and standard deviation. So fingers crossed, and let's press enter. Yeah, 0.5 means we have covered half the area under the curve by using the true option in the norm.dist formula, which is satisfying to know because our formula is working well. So I'll just copy this formula all the way up so that we get the area under the curve to different points till here. Okay, and I'll also copy it all the way down, and at the last point I should see that the area covered under the curve till the last point should be almost equal to 1. Yeah, and we see it's reach 1 by the time x is equal to 35.4, because after that the remaining area is so negligible that we can safely say that all the area has been covered till the value x equal to 35.4. So what it means in terms of the graph is that by the time you reach 35.4, okay, something going wrong here. A second. Yeah, by the time you reach x equals to 35.4, this should be 35.4. After that, the area under the curve is negligible. So you can safely say that if you cover all the area till here, including this, everything, you have covered 100% of the area under the curve. Okay. And if you don't want to use the built-in Excel formula to calculate the area up to a point, there's another way. So just to explain it, let me delete this figure first. Okay, let me select it. Yeah, let me get rid of it, and then let me choose the pen again. And we have our distribution, and we have already broken up the distribution into small intervals here, as we can see in our column E starting from row number 9, right? And we have the areas for each of these small rectangles. So now let's say if I want to find what is the area till x equals to 25, which is over here, all I have to do is add up the area of each of these small rectangles till 25, right? So that's what I'm going to do. Let me switch back to the cursor, and for the first rectangle I'm just going to take this area that we have till here, and from the second rectangle onwards I'm going to add the area covered till the previous rectangle plus the area of one more rectangle, and this is how it is going to follow. This equals to the area till this rectangle plus the area of this rectangle, and I'm just going to drag it down. So again, let's go and check what's the area covered till x equals to 25 for this one. Okay, where is 25? Here it is. So you can see again we have 0.5, which is half. We have covered half the area under the curve by the value x equals to 25. So it's the same whether you want to use the inbuilt Excel formula with the true option, or whether you want to calculate the area of the individual rectangles and add them up yourself, the result that you get is the same. So you can see it's the same for all values of x. It's the same. Okay. And one last thing that I want to mention is that this area that you take up to a point x, if I just plot it, let me insert a chart, line chart, so you can see this area. So as we move along the values of x, initially the area is close to 0, and as we go further the area under the curve keeps increasing, and as we reach higher values of x, the area under the curve touches 1 and it stays at 1. Don't let these values of x confuse you, because as I had mentioned earlier, by default when you plot a chart, Excel just shows you the serial number of the observation. Let's just go to select data, and for our horizontal categories, let's just choose, yeah, let's, and, yeah, okay, yeah, now we have the correct value. So you see, by the time we reach x equals to 25, and let me just use my pen again, by the time we reach x equals to 25, which is somewhere here, and go up, you can see that the corresponding area covered is half, 0.5. And this curve that you see here is commonly known as the CDF, that is the cumulative density function. So in summary, if you use the false option with the norm-based formula, you get the probability density function known as the PDF. And if you use the formula with the true option, then you get the cumulative density function, which is the CDF. And as a last step, I just want to go and show you what the Excel documentation has to say about the last Boolean parameter that we have just seen. Okay, so this is the help for the norm.this function, and the last parameter which we were entering as either true or false, that is what it calls cumulative. And let's see the definition of cumulative over here. So it says that a logical value that determines the form of the function. If the cumulative is true, norm.this returns the cumulative distribution function, or it is also called the cumulative density function. If false, it returns the probability density function. So just by reading this, you wouldn't know what it means, but after having gone through the charts and the formulae and see how they work out in the Excel, you'll probably have a better understanding of what the true and false options mean. So now, having gone through so much of theory and having seen so many charts and formulae, the video would be kind of incomplete if we did not see a practical utility of normal distribution. So let's go ahead and take a look at what could probably be called a real life example, and how we can use the normal distribution to address a real life situation. So let's say you are working in the city planning department, and your city has enough capacity to harvest rainwater if the rainfall in your city is up to 26.2 centimeters. 26.2 centimeters is what I'm marking here. And you see, using your cumulative distribution function, that at 26.2 centimeters, the probability that the rain is going to be up till 26.2 centimeters in a given year is 60%. What you see here, 0.6. So it's a 60% chance that the rainfall in a particular year is going to be 26.2 centimeters. So there is a 40% chance that it is going to be more than 26.2 centimeters. So as a city planner, you know that you are leaving 40% to chance. You are not equipped to harvest the rainfall if there is more than 26.2 centimeters of rain, and you are not comfortable with that. You don't want to leave more than 20% to chance. If required, you are willing to invest to increase the rainwater harvesting capacity of your city. So if you don't want to leave more than 20% to chance, means that you have to prepare for 80% chance. So you check at 80%, the amount of rainfall that you can expect at 80% confidence is 29.4 centimeters. So as a city planner, you have realized that you need to increase the rainwater harvesting capacity from 26.2 centimeters to 29.4 centimeters if you don't want to leave anything more than 20% to chance. So that is perhaps a real life example where you can use the normal distribution. All right, guys, then this is about it with the normal distribution. There are perhaps some topics that I have not covered in this video. For example, the standard normal distribution, but this video has turned out to be quite lengthy already, and I don't want it to be any more lengthier. So if you find that the content in this video was useful to you, then please go ahead and like the video. And if you think it can be of help to somebody else, so please share it with them. Thanks for your time. Hope to see you in the next video. Bye.